Hello everyone, and welcome to this video short, where we are going to continue our time complexity analysis and runtime analysis of some sorting code. In our previous example, we went through, line by line, code associated with an inefficient variation of bubble sort. At the end of our line-by-line analysis, we derived a step count function t of n, which was quadratic in nature. We also identified that there was some unnecessary iteration going on here within this bubble sort variation. Specifically, we identified that after one of the iterations completes, we no longer need to scan the entire length of the array because the lightest or heaviest item is always bubbled up or bubbled down to the correct final destination within the sorted list. Thus, we don't need to iterate to the end of the list in the next follow-up sweep. So we can improve that in our correct version of bubble sort. We will then do time complexity analysis and then measure the actual runtime to see if we get the true gains that our theoretical assessments imply. So in our new version of bubble sort here, the general structure of the code is the same and the idea is the same, and that we're going to, again, try to bubble up the lightest or the heaviest, the values up into place so that we get a sorted list. However, in this scheme here, we are going to have our double looping structure, our embedded looping structure, where the inner loop is going to depend on the outer loop's variable, where the outer loop's variable is going to decrease by 1 during each iteration, indicating that the item at the end of the list is now in its final resting place, so there's no need to iterate to the end of the list or that nth item in the list. And that's going to decrement each time we iterate and each time we run this outer loop. Therefore, the total number of computational steps associated with the inner loop should decrease, and we can now count to try to identify how much it's going to decrease by. So again, going line by line, again we have constant number of operations, linear number of operations. Now, when we get to this line of code here, we see that we have our loop inside of the loop. We know that we have a looping structure here that is going to iterate n minus 1 times. However, n is actually going to change during each one of the outermost iterations. So what does this mean? Well, the first time this outer loop runs, it's going to, or the first time this outer loop runs, this inner loop is going to iterate n times. And then the next run, it's going to iterate n minus 1 times. And then the next run, it's going to iterate n minus 2 times. And the next run is going to iterate n minus 3 times, and on and on and on, all the way down to 1. So we're going to get this total number of computational steps associated with this line, proportionally speaking. Note that this is a very common series in discrete mathematics, which evaluates to n times n minus 1 over 2. So again, we have a quadratic term here, but note that it's about half the number of steps, as compared to our previous version of the sorting code. So for these lines of code associated with the innermost loop, we will estimate that we have approximately n times n minus 1 over 2 computational steps. Again, I noted that, and I should say that I've kept this over 2 or the 0.5 for comparison purposes so that we can compare line by line with the code above. Otherwise, this could simply be absorbed into our constant c. What does this mean at the end of the day? Well, when we derive our step count function and simplify, we're going to get something that looks very similar to our older version of bubble sort, except we're going to have half the number of computational steps associated with this term here, approximately speaking. So, are we going to see that when we run our experimental trial? That's the question we want to answer. So, in theory, we again have a sorting algorithm that is quadratic in nature, but if we go count by count, it looks like we should have only half of the number of computational steps, approximately half the number of computational steps associated with this improved version of the code. So let's test it out. Let's run some trials where we run both sorting algorithms on lists of varying sizes. That way we can identify the runtimes associated with different or varying sizes of input for each of the algorithms. We can then plot the results and compare the results for each. Right? And so that's what this final chunk is for. So we are going to vary our input sizes, that is the length of the lists to be sorted, all the way up to 10,000. And we're going to start and run these trials in 1,000 increments. Right, so here's our looping structure for that. We randomly generate the lists, and then we time the sort. So we start the timer, run our inefficient sorting algorithm, and then stop the timer and store the value in an array so that we can plot it later. So that's the total runtime associated with the first run of our trials. Right. We can then run on the more efficient version of bubble sort, where we start, call bubble sort, and then store the value here. All right. Then we have some results to plot, right, once the trials are completed. Right. At the end of the day, when we run this, note here, this is the plot that I get. You guys might get slightly different ones when you run these on your machines, as there's a number of different factors that can affect actual runtimes as compared to theoretical time complexity. But as we can see here, we do get approximately double the speed up with our improved code as compared to the slower version of the code. This can be clearly seen here when the input size increases. Right, so our slower sorting algorithm, for example, for an input size approaching 10,000, right, is about approaching 15 seconds for the slower version, where it's more like 9 seconds for the faster version, or the improved version. Also note here that we do, of course, have an improvement with our improved code, as indicated and as implied by our theoretical analysis. So it's great to see that we have some real world and real life gains, measurable gains, when we execute our code. But we can also confirm from our theoretical analysis that both of these curves look approximately quadratic, as the runtime does seem to scale quadratically with respect to the size of the input for both. It's just the quadratic curve is a little bit flatter for our improved and more efficient code. All right, well, thank you for joining me in this example. Again, I always think it's great to be able to confirm theoretical analysis with some actual experimental trials and some measurable results. Thanks for joining me, and I'll see you in the next episode.